So today we will continue the topic of tensor products. So first we will see the relation between the direct sum and the tensor product. So what is the proposition? Let's say M is a direct sum of Mi, and here we have let's say I is varying from 1 to n. So you can see this is M1 direct sum up to so on Mn. So so this is an R module, and N is also an R module, and it is a direct sum of Nj. Nj is varying from 1 to let's say M, और यहाँ पे so this thing is equal to N1 direct sum up to so on Nm. So what is the point that M tensor N? So in this case, I will take the direct sum of so Mi into Ng, tensor Ng, एंड यहाँ पे जो इंडेक्सिंग चल रही होगी तो वो आई जे से चल रही होगी, दो से चल रही होगी, एंड ये जा रही होगी एम एन के ऊपर जा रही है, टू सेवन एम एन। बिकॉज हम हर जैसे हम प्रोडक्ट लेते हैं तो इसी तरह हम हर एक कंपोनेंट का दूसरे के तमाम कंपोनेंट के साथ टेंसर प्रोडक्ट लेते हैं। So in this way, and this result holds up to the isomorphism. So here we have isomorphism. So proof का idea है that what is the proof? So in this case, अच्छा मैं एक before the proof एक remark देना चाह रहा था कि जो last हम लोग कुछ proof कर रहे थे कि sometimes in order to show that there exists a linear map from the tensor product to an R module, uh, we usually use the universal property of the tensor product for the existence of a linear map. For example, इस remark के तौर पर देखें, in so in the proposition we need to prove that M tensor N and it is isomorphic to N tensor M. So for this purpose, just मैंने कहा था कि that take a map, let's say F, which is from M tensor N to N tensor N in this way, such that X tensor Y move करो to Y tensor X, and this should be an R linear map. तो अब इसको sometimes difficult होता है R linear map proof करना, तो हम just क्या property use करते हैं, so for the existence of this map F, that there exists R linear map in this way, so we will use a universal property of the tensor product. So for example, we have M cross N and N tensor N. So and this is a bilinear map theta. So let's say G is a map G, which is defined in this way, that M cross N का जो output होगा, it is equal to N tensor N. So universal property of the tensor product will guarantee that there exists, will give us uh, or shows that there exists, or the universal property of the tensor product implies that there exists a bilinear map, a unique bilinear map F, such that M tensor N, the output of the N tensor M is N tensor M. So this thing just simply shows that this F is already a linear map. So you don't need to show that this F is a linear map. Why? Because you just need to check that this M cross N, this map is a bilinear map. Because if this map is a bilinear map, then the universal property of the tensor product will automatically implies that this map, which is the required map, जो हम लोग कंस्ट्रक्ट करना चाह रहे थे, this map is a linear map. So in and this map is already satisfying this property. So what is the property that if theta, first we apply theta and then f, so it is equal to uh, it is equal to g. In the same way, if I want to construct this thing, if I want to construct a map from in this way, so again I will use the universal property of the tensor product, said that if n cross m to m tensor n, let's say this map it is equal to uh, h, and this map is a and one can prove that this map is a bilinear map. So and there exists theta dash here. So the universal property of the tensor product implies that there exists G such that n tensor m के जो इमेज होगा it is equal to n tensor m. So G and this G is a linear map. So from the universal property of the tensor product, we automatically implies that M tensor, the image of M tensor n, it is equal. So G is uh, going from M tensor n to M tensor n, and G is already a linear map which is defined in this. And say that this diagram is commutative. That is, first we apply uh, uh, theta bar. ओके, इस वाले को जी का नाम दे दें, इस वाले को आप लेट्स से टी का नाम दें, तो जी ऑलरेडी यूज कर चुके. So T is a linear map, so, and this is equal to H. So now we already have two maps, G and H, which are linear map, and it is not, uh, and it is very, and both are linear maps. So now it is very easy to show that both are in inverse of each other. So which implies that G and H both are isomorphism, and n tensor n is isomorphic to n tensor n. तो यहाँ पे मैं इन प्रॉपर्टीज को यूज करने की जरूरत भी नहीं है, बिकॉज ये दोनों मैप जैसे मैंने डिफाइन किए थे, यू कैन चेक इजली दैट दे आर इनवर्स ऑफ ईच अदर, बिकॉज फर्स्ट मैप इज how can we define the first map G, that image of M tensor n is equal to n tensor n. So just switch होनी है position. So ये एक remark था. So this is a way to define. In this way, we can define an R linear map from M10 to an R module. So what is the thing that you can check easily that if we take the composition, then I will get the identity of M10, and if I take the composition of G and H, then I will get the identity of N10. So it implies that G or sorry T. Here we have T. It implies that G or T is an isomorphism, which implies that M tensor N is an R module. It is isomorphic to N tensor. So ये remark मैं इस वजह से बता रहा हूँ because in this proof we will so we want to prove this theorem that if M is a direct product of M1 up to so on Mn, and N is a direct sum, sorry, direct sum of M1 up to Mn, and N is a direct sum of N1 up to Nn, then M tensor N is a direct sum of Mi tensor Nj, where I and J, so they are varying up to Mn. So what is the proof of this proposition? So again, let's say we have a map uh, M cross N to this thing, and Ij is varying from to Mn, and this map is defined in this way, that if input is Mn, so we know that if M is an element of N, so अब ये map किस तरह define हो रहा है? We know that if M is an element of N, then M, uh, but M is a direct sum of Mi. So therefore, we can write M in this way. It is summation of, so it is x1 up to so on xn. It could be written summation of xi, and each xi is an element of Mn. And I is varying, and here I is varying from 1 to n. And the same way, if n is an element of n, which is a direct sum of nj, j is varying from 1 to n. So it implies that n it is equal to y1 up to so on yn. So summation of yj, and where y is varying from 1 to n, and each yj it is an element of nk, and k is varying from 1 to n. So what is the point that this thing actually Mn, uh, so this component Mn could also be written in this way, that this is a summation of xi and this is a summation of yj. So now they are defining a map, this map F, और F map किस तरह से डिफाइन होता है, that image of summation of xi. तो हम जस्ट क्या करेंगे, हर एक एक्सरसाइज का वाई बेस के साथ टेंसर प्रोडक्ट लेंगे और उनका सम लेंगे. तो दिस मैप इज डिफाइंड इन दिस वे, which come here that it is the direct sum of or it is a sum of xi tensor yj, where ij is varying to zone mm. So map F is defined in this way. So we already have a bilinear map from M cross N. uh, और जो बाइलिंगुअल मैप क्या होता था कि m cross n को m टेंसर n में ले आता था. So the universal property of the tensor product will imply that there exists a linear map. There exists a linear map. There exists a linear map G, a unique linear map G, such that image of M tensor N it is equal to summation of xi tensor yj, where ij is varying up to n. So, and we already know that G is a and we already know that G is a linear map. तो आपको चेक करने की जरूरत नहीं. हाँ सिर्फ आप लोग को ये चेक करने की जरूरत होगी जो मैंने किया नहीं लास्ट एग्जाम्पल में कहता that you need to show that this F is a bilinear map. लास्ट एग्जाम्पल जो रिमार्क दिया था उसमें तो बहुत इजी था. But here you can also check that easy that this F is a bilinear map. So it automatically implies that this G is a linear map. So now we have a linear map G from M tensor N uh, to this thing. Uh, Now we need to do or we need to find out uh, the inverse of G, which is also an R linear map. तो उसको यहाँ पे तो हमने जस्ट हमने यूनिवर्सल प्रॉपर्टी ऑफ यूज कर ली थी टेंसर प्रोडक्ट की टू कंस्ट्रक्ट दिस थिंग टू कंस्ट्रक्ट दिस मैप. अब हम रिवर्स मैप क्रिएट करेंगे. So let's say you can in this step uh, we will construct an R linear map uh, and that R linear map is H from this thing. Okay. So in the construction that first we can see that we have to since each mi each mi is a sub module. So each mi is an since it's a direct sum, so each is a right is an R sub module of M. Therefore, there exists an inclusion map uh, from MI to M. And how inclusion map is working that if input is equal to xi, then output is also equal to xi. So, and in the same way, uh, one can see that nj uh, is an R submodule of M. And so there exists an inclusion map H from nj to n, and it is defined in this way. So now we can extend we can define actually. So they will induce. So both I and J induce and this inclusion map is again an R linear map. So I and J. So these map yes को आप I tilde कर लें ताकि आप सब इसके so I tilde J tilde induces an R linear map. Let's say आप इसको T tilde नाम कर दें an R linear map T tilde in this way from Mi tensor product Nj to M tensor N. Simply in this way that Xi tensor Yj का जो इमेज होगा ये यहीं पे Xi tensor Yj equal होगा. And then we can extend this map because अब ये जो map है T so it is defined on each component. So we can extend uh, T bar to an R linear map H which is going from this way and here elements are in the form of sums and this is equal to Xi. Uh, 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 okay, so again this is equal to summation of तो यहाँ पे जस्ट मैप एक हो जाता है MINJ और ये लीनियर मैप इंट्रोड्यूस करवा देगी. अच्छा और ये जो लीनियर मैप होगा बिकॉज यहाँ पे जस्ट क्या था Xi so this thing. So what is the point that we just use inclusion map? So we just use the idea that since Mi and Nj are submodules, so with the help, so we have an inclusion R linear homomorphism. So with the help of this inclusion R linear homomorphism, one can check easily that this it induces an R linear map uh, from Mi tensor Nj to M tensor N in this case. So again, you can see that this you can see this bar as an T tilde as an inclusion map. So now this inclusion map, so this inclusion map uh, is defined on each component of this thing because हमें यहाँ से मैप ट्रांसफर कर रहा था. So inclusion map is defined on each component of this whole module. तो ये पूरा R मॉड्यूल था और उसके हर एक कंपोनेंट में डिफाइन कराया था. So what we did, we that and it is defined in this way. It is Xi tensor Yj. And what we did, we just extended this map from this module to this module in this way that just मैंने अगर यहाँ के elements का जब sum किया so it will give so वो just क्या आंसर देगा ये वाला आंसर देगा. So again we don't need to check that this is a दिस इज एन आर लीनियर मैप. तो हमने कंस्ट्रक्शन भी इसी वजह से करी थी. मैं डायरेक्ट भी डिफाइन करवा सकता था बट ये कंस्ट्रक्शन हमने इसी वजह से करी थी बिकॉज आई जस्ट वांट टू शो दैट आफ्टर द कंस्ट्रक्शन we will get an R linear map. So now we have two maps. First map is G, which is from M tensor N to this thing, and also we have H, which is from this direct sum of Mi tensor Nj to Mn M direct M tensor N. So G is from M tensor N to the direct sum, and H is from the direct sum to M tensor N. So and G is defined in this way that uh, so अब मैं इन दोनों का composition compute करेंगे, directly compute करेंगे that what is the composition. So here H composition की मैं जब Mn put करूँगा तो first मुझे G को उसके Mn को अपने components में pick करना होगा. तो अगेन सिर्फ डेफिनेशन के थ्रू उनकी आ जाएगा, इतना डिफिकल्ट नहीं है. तो this summation of xi is summation of yj, and how g is defined, so it is equal to summation of, because जो हमने g के लिए एक्सप्रेशन निकाला था, तो ये एक्सप्रेशन हमने g के लिए निकाला है, that m tensor n, and sorry this is m tensor n. So this summation of ij mi tensor nj, and if we apply h, which is defined here, so it is summation of mi tensor of summation of nj, sorry मैं एक्साइज यूज करूँ उसके लिए, पता नहीं यहाँ पे जी को एक्साइज यूज करूँ. So if we apply g, so this is summation of ij and xi tensor yj, and if we apply f, so again I will get summation of xi tensor of summation of yj, and this is equal to x, and this is equal to y. तो यहाँ पे हमें x tensor y से स्टार्ट करना है. So if we plug x tensor y in H composition G, so first we will break x into its component, and then we will break y into its component. So I will get this thing, and now if I apply G, so G is applied in this way, and then H is applied in this way, so I will get x tensor y. So in the same way, if we compute G composition H into summation of xi tensor yj. So first we will apply h. So what I will get summation of xi tensor summation of yj, and then if we apply g, so again we will get summation of ij xi tensor yj. So the first computation shows that H composition G is the identity of M tensor N, and the second computation shows you that G composition H, this is the identity of this thing. So both thing. So in the end, we will get this condition that G is an isomorphism, and then G is an isomorphism, which implies that M tensor N, it is isomorphic to this. Okay, so there is a corollary uh, of this thing, which shows that the tensor product of free module is a free module. So let Mn be free modules.
सर थोड़ा सा ऊपर करेंगे प्लीज.
Oh,
ओके थैंक यू.
so let Mn be free modules.
और थोड़ा सा ऊपर कर देगा.
अच्छा, मैं पहले आप लोग के लिए कॉपी कर लें, फिर मैं अब बता देगा आप लोग जब कॉपी कर.
आई हैव डन सर.
Okay. So let Mn free module with basis x1 up to so on xn, that is rank of uh, m, it is equal to n. जैसे हमारे पास डायमेंशन होती है इन द केस ऑफ वेक्टर स्पेस. So in the case of free modules, if M is a free module, that is M admits a basis set, then the cardinality of the basis set is called the rank. In the case of the vector spaces, the cardinality of the basis set uh, is called the dimension of a vector space. But in the case of modules, the cardinality of the basis set uh, for a free module M, it is the rank of that free module. So here I am assuming that and so n is also a free module with basis y1 up to yn. That is, uh, we can assume that rank of n is equal to m. Then what is the claim? Then m tensor n is also a free R module uh, with basis. की basis क्या होगी? So again, it will be the mutual product, mutual tensor product, and where ij is varying from mn. Mutual product means that we will take the tensor product of x1 with every element of this set, x1 with y1, y2 to so on yn. In the same way, we will take the tensor product of xn with every element in this basis set. So that's why cardinality of this basis set is equal to mn. So so here elements are in this way that it is from x1 tensor y1, x1 tensor y2 up to so on. In the end, we will get this situation that xn tensor y. So it automatically implies that what would be the rank of m tensor n? It is mn.
Amen.
So again, what is the proof? By definition, by the definition of free module, so every free module we can break as a direct sum of free as a direct sum of free cyclic modules. So we know that from the definition that every the m we can break m in this form or simply n which is generated by these cyclic free modules. Uh, or you can assume that these are free cyclic or sub modules भी कह सकते हैं. These are free cyclic sub modules. In the same way, n we can break n in this way. Uh, where these yj's are also free cyclic submodules. So if we take the m tensor n, then using the previous theorem, so here I is varying, from 1 to n, and here j is varying from 1 to n. So using the previous theorem, we can say that this is the direct sum of ij mn and and up to so on. You can say that okay, and okay, and up to and moreover up to the isomorphism, we know that each this thing that each free cyclic module is isomorphic to R. So this is also isomorphic to R. So in the end, you will see that this is isomorphic to R raised to the power uh, n, and this would be isomorphic to R raised to the power n, R raised to the power n. So in the end, you will see that each component here. So that's why अब मैं जो डायरेक्ट सम अप्लाई करूंगा वो इस चीज पे अप्लाई करूंगा. So m tensor n uh, it is equal to Rn tensor Rm, and using and what is the meaning of Rm or isomorphic बल्कि कहेंगे, it is isomorphic to Rm. And what is the meaning of Rm thing? So actually it is the direct sum of R n times. So I is running from 1 to n. And what is Rm? It is a direct sum of Rm. And here in the second component, R is running from K from 1 to n. So using the previous theorem, we can say that this thing actually is equal to the direct sum of ij up to mn, and it is equal to and this thing is equal to r because every component is equal to r. So जब हम so so that's why and this thing is automatically equal to r raised to the power mn. So in the end, we prove that m tensor n uh, m tensor n is isomorphic to r raised to the power mn. So which implies that m tensor n is a free module of rank mn. थोड़ा सा इसके प्रूफ को और एलिब्रेट भी कर सकते हैं because I just use the fact that each cyclic module. So here I use the fact that M could be decomposed into a direct sum of free cyclic module, and we know that every free cyclic module is isomorphic to R. So that's why I just proved that. So initially, अगर मैं यहाँ से so initially what we have seen that this thing is just equal to the direct sum of or isomorphic to the direct sum of free cyclic module. So it is a direct sum of these R, which is R raised to the power m n. And again in this case, it is isomorphic to direct sum of uh, R and here J is running from 1 to n, so which is equal to Rn. So what we proved that m times Rn would be isomorphic to R mn, which shows that m times Rn is a free module of rank mn. बट मोर ओवर यू कैन ऑल्सो प्रूव दैट हमारा जो क्लेम था वो ये कि दैट दिस सेट व्हाट इज द क्लेम दैट दिस सेट जो हमारा क्लेम था दैट दिस सेट so if this set is a basis of m and this set is a basis of n, then this set which we define in this way, so it is a basis of m tensor n. तो इसको भी थोड़ा सा हम एलिब्रेट कर लेते हैं, इसको किस तरह से शो करेंगे. So again, we know uh, that m could be we can break m as a direct sum of three cyclic modules, and where each so that's why and each and n could also be and we can also break n as a direct product of free cyclic modules, and here each free cyclic module xi, so it is isomorphic to R, and again cyclic module free cyclic module Ri is also isomorphic to R. So M tensor n, and why because and why this thing holds because the set f x1 up to xn is a basis. So basis set means that m could be generated with the help of x1 up to xn, and n could be generated with the help of y1 up to yn. So in this case, that's why m could be break in this way, and n could be we can break n in this way, and we can break n in this way. Now m tensor n, sorry,
सर y के साथ j ही है ना, I तो नहीं है ना?
sorry, j है, sorry, y के साथ j है। तो ये वाला प्रूफ है, ये मैं ज़्यादा आपको एलिब्रेट करके बता रहा हूँ क्योंकि लास्ट प्रूफ में सिर्फ आपको ये शो किया था कि वो उसका सिर्फ जो दैट एम टेंसर एन वुड बी अ फ्री मॉड्यूल, but now this proof shows you that m tensor n it would be a free module with basis xi tensor yj varying up to mn. So m tensor n, uh, so and since m is generated by xi's, and these xi's the set and this set is a basis set of m, and n is generated by yj's, and the set yj's is a basis of n. So that's why m tensor n. So initially, m tensor n could be written in this way. It is the direct sum of xi tensor and I is running from 1 to n tensor यहाँ तक तो प्रूफ सेम है। अब ये नाउ यूजिंग using the last proposition up to the isomorphism, it is equal to the direct sum of uh, ij is varying up to mn and the tensor product of xi tensor of yj. ओके, नाउ हम हर एक कंपोनेंट को एनालाइज करेंगे कि हर एक कंपोनेंट हमें किस फॉर्म में दिखता है। सो हियर a typical component in this form, and again you can say that these are free cyclic modules, free cyclic submodules. So we have this thing,
सर वाई आई के साथ सम क्यों हो गया?
सॉरी ये मैं इसको लिखना भूल गया, मैंने डायरेक्ट हमको असल में डायरेक्ट हमको समझ ली।
सही।
So j is running from 1 to n and summation of yj. So whenever I will analyze a typical component uh, this way, so this thing actually it is uh, up now here the first component is isomorphic to R and the second component is isomorphic to R. So this thing would be isomorphic to R tensor R, and this thing in the end this thing is also isomorphic to R. Why this thing is isomorphic to R? Because हमने ये चीज पढ़ी है कि R tensor M it is isomorphic to 1. So if we take the product of R tensor M with M, it is equal to 1. So in the way अगर मैं इस component को M fix कर लूँ and I will take the product of R tensor M with this thing, so in the end this thing uh, would be isomorphic to R. Okay, so ये तो रीजन मैंने पहले ही बताया था कि हर एक कंपोनेंट अगर R के आइसोमॉर्फिक आ गया तो इन द एंड अप टू द आइसोमॉर्फिज्म आपको ये किसके आइसोमॉर्फिक आ जाएगा, डायरेक्ट प्रोडक्ट ऑफ आई के फ्रॉम वैनिंग टू एम एन। तो ये जस्ट पूरा का पूरा R के आइसोमॉर्फिक आ जाएगा, एंड विच वुड बी इन द एंड इक्वल टू R रेज़ टू द पावर n। ये तो जस्ट पहले भी मैंने आपको प्रूफ करके बता दिया था कि हर एक कंपोनेंट R के बराबर होगा। But we can say one more thing about this component. तो ये शायद आप लोग को थोड़ा सा प्रूफ भी देखना पड़े, that if we take the direct product or the tensor product of this component xi with yj, so this thing is also equal to the cyclic module generated by xi tensor yj. So xi tensor yj. And how can we prove this thing? Because here in this case, if I want to prove that these two things are isomorphic, so in the first case, elements are in this form. कि यहाँ पे जो f map jar होगा, so here element are scalar multiples of xi, and also here it is a here scalar multiple of yj. So if so the output it is equal to alpha beta xi tensor yj, and we can so under this map this thing is an isomorphism, because how can we define G? So F is defined in this way, and G would be defined in the reverse way. So in the case of G, so every element is a scalar multiple of xi tensor yj, and here scalar it is equal to R. So here all alpha, beta, gamma they are in R. So and what is the image? So we can multiply scalar with any component. So it is defined in this way, that it is equal to gamma Rx xi tensor yj, which is also equal to xi tensor R yj. Now just try to check that f composition G it is equal to the identity, and G composition F is also equal to the identity. So in the end, we can easily show that this thing is isomorphic to this thing. So in the first part, what we proved that the tensor product of xi of the cyclic module generated by xi with the cyclic module generated by yj, it is isomorphic to R. And in the tensor part, in the second part, we will see that the tensor product of the cyclic module generated by xi with the cyclic module generated by yj, it is equal to the cyclic module generated by xi tensor yj. So what we can see that, so in this picture, what we can see in the end, that xi tensor yj it is isomorphic to R. So in this case, uh, what we proved that M tensor n uh, could be decomposed in this way. M tensor n could be decomposed in this way, where x tensor I, because this thing implies that ये वाला जो cyclic module था, because if cyclic module is isomorphic to I, so it implies that cyclic uh, uh, submodule xi tensor yj is a free R module. So in the end, we proved that uh, M10 could be decomposed in this way. And here, in each case, this thing actually uh, this and each component is a free cyclic module. So we know that if a module could be decomposed into a direct product of free cyclic module, then this module would be a free module. So it implies that M10 is a free module with basis x I tensor yj, and this is varying up to ml. So this is a proof. So in the first part, तो जो first मैंने proof किया था, so ये proof okay था, because here I decompose into the component into cyclic R module, and each component is isomorphic to R. So in the end, we will see that M tensor n, it is isomorphic to R raised to the power mn. Uh, but more precisely, the second proof shows you that this is a free cyclic R module with this uh, with basis this type. And this also proved that the rank of M tensor n, it is equal to m. So यहाँ पे अब हम लोग का जो टेंसर प्रोडक्ट का जो टॉपिक है उसको मैं यहाँ पे क्लोज कर रहा हूँ। चीज़ें इसमें और भी हैं, और जस्ट एक आइडिया है कि एक एप्लीकेशन है टेंसर प्रोडक्ट की, दैट ओके, हम लोगों ने वैसे तो डिस्कस किया था कि कंप्यूट करने के लिए या कुछ मैप को बाइलिनियर मैप करने के लिए या एक्सेस करने के लिए काम आ रहा है, बट एक आइडिया है एक्सटेंशन ऑफ स्केलर्स का। तो एंड दिस इज a direct application of the tensor product. ओके, सो एक एग्जांपल से स्टार्ट करते हैं। ओके, सपोज m इज अ z मॉड्यूल, कोई सा भी z मॉड्यूल है, तो आप q ले लें, r ले लें, c ले लें, कोई सा भी ले लें, z3 ले लें, तो m इज अ z मॉड्यूल। चलो z3 ले लेते हैं ज़्यादा, तो z3 इज अ z मॉड्यूल। Now we also know that as a ring uh, that actually it is a subset of Z iota, and there is exists an inclusion map. So now what is the problem that could be considered? Z3 as a Z iota module. So what is the point that here scalars are expanding. So initially a Z is the set of scalars, and now I want to extend the set of scalars up to Z iota. So this is the point that we could be considered C3 as a Z iota module. So this is the point. So in this case, uh, uh, so we can solve problem with the help of tensor product. How can we solve this problem with the help of tensor product? So we know that uh, Z iota. Uh, it
Z3
also
tensor Z.
Yes.
Isomorph.
Yes. Z iota is also a Z module. So therefore, we can take the tensor product of this Z iota, because this Z iota is a Z module, and we also know that Z3 and we also know that Z3 is a Z module. Okay, so we will take the tensor product of Z iota uh, with C with Z3. Okay, now what is my claim that this new module, ठीक है, इस मॉड्यूल को जस्ट मैंने नाम दे दिया कि लेट्स इस मॉड्यूल को मैंने टी नाम दे दिया. तो टी इज अ जी आयोटा मॉड्यूल. और इसको मैं जी आयोटा मॉड्यूल किस तरह से कंसिडर कर सकता हूँ, बिकॉज whenever I will take alpha from z iota and take a typical element from t, which is in the form of a tensor b, where a is an element of z iota and b is an element of z3, then what I can do, इसको हम बाद में किसी सिंपल फॉर्म में करेंगे, बट डिफाइन इस तरह से होता है. So we can take the tensor product of alpha with A tensor B by just multiplying alpha with the first component. So in this way, so this is the definition of the scalar multiplication. So under this scalar multiplication, this T, is a Z iota module. So I will say that मैंने अब स्केलर और कुछ वर्ड्स में ये भी कहते हैं कि मैंने अब Z3 को Z iota मॉड्यूल कंसिडर कर लिया. So although up now not I am not working with Z3, I am working with T. But here we will say that हमने क्या कर दिया, इसके जो स्केलर्स हैं उनको एक्सटेंड कर दिया. So this is the idea of एक्सटेंशन. तो वो अलग बात है कि आप अगर इस मॉड्यूल को आप किसी और बेहतर फॉर्म में निकाल लें, लेट्स से अगर आप इसको कुछ स्केलर्स को मूव करके मे बी Z3 आएगा की फॉर्म में निकाल लें, तो वो इस फॉर्म में निकल आएगा. बट जनरल प्रोसीजर ये है. So what is the general procedure that if so let M be an R module uh, and R is a subring of S. So we can extend uh, the set of scalars to S in this way that uh, since R is a subring, we can extend the in the following way. Since S is an R module and M is also an R module, therefore T is defined in this way. Therefore T it is equal to the tensor product of S with M as an R module. So now this T uh, is an S module under the following scalar multiplication. And what is a scalar multiplication? That if S is an element of S and A tensor B, it is a typical element in T which is equal to S tensor M. So here we know that A is an element of S and B is an element of M. And then S into A tensor B, it is equal to S of A tensor B. So under this scalar multiplication, we can consider this T uh, uh, as an S module, and here we constructed a module which could be considered as an S module. तो इस मेथड से हमने क्या कर दिया, इसको एक्सटेंड कर दिया. वो अलग बात है कि जैसे हमने इस एग्जांपल में देखा था कि आप इसको सिंप्लीफाई करके और एक सिंपल सब मॉड्यूल के अंदर भी राइट कर सकते हैं. आई थिंक इस वाले मॉड्यूल को आप कंप्यूट करेंगे तो प्रॉब्ली यू विल गेट C3 आएगा. एंड जैसे कि टेंसर मोनोमियल्स को कंप्यूट करें तो जैसे फॉर्म में आपको नजर आ रहा है. Now we also have an idea of the restriction of scalars. We can also restrict the scalars. So let's say let M be an S module and phi from R to S is a ring homomorphism. So R is also a ring, is a ring homomorphism. Phi from R to S. So in this case, if in अगर आप inclusion map को consider करें, inclusion map is also a ring homomorphism. So through the inclusion map, you can also consider that R is a subring of S. But in general, phi is a ring homomorphism. So what is an idea that we can consider M also 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 uh, an R module. तो किस तरह से कंसिडर कर सकते हैं अंडर द फॉलोइंग scalar multiplication. And what is a scalar multiplication? Let's say if R is an element of R and X is an element of M, then R dot X. So if R is an element of R, so, and we know that phi is a homomorphism from R to S, so we know that R किस में मैप होगा, phi of R में, which is an element in S. So how R dot X is defined? It is defined in this way that we will take the image of R, which is an element of S, and we will take the product of S with X, which is an element of in M, which is an element in M. So again, this is we assume that M is an S module. So in the end, you will get this thing. It is an element in M. So the scalar multiplication is defined in this way that if we take the scalar multiplication of R with X, so I will just take the image of R under phi and multiply with X. So in this way, I can consider M as an R module. So we can see this thing uh, in this way that suppose let M uh, be a Z module, कोई सा भी Z module, and we know that there exists and we know that there exists a natural homomorphism phi from Z to uh, Z3 in this way that whenever input it is equal to, let's say, R, then output it is equal to the equivalence the class of R. So uh, M is also a Z3 module in this way that if you multiply okay, so sorry, initially M is a Z3 module. मैं इसको कहता उसको C मॉड्यूल किस तरह से कर सकते हैं that M initially Z3 module और ये थी तो M is also we can M is also a Z module. That if we multiply an integer so with some element of module, so it is just equal to R phi into M. So ये reverse process है just if M it is a Z3 module, so in this way I can also consider M as a Z module. ओके क्लास, तो यहाँ पे मैं लेक्चर एंड कर रहा हूँ, तो नेक्स्ट क्लास में हम लोग नया टॉपिक स्टार्ट करेंगे शॉर्ट एग्जैक्ट सीक्वेंसेस का जो लीड करेगा प्रोजेक्टिव मॉड्यूल्स के आगे को. ओके, थैंक यू. एनी प्रॉब्लम?
Okay, thank you, sir.
Thank you, sir.
Allah Hafiz.
Love this.
Uh,